Hi, I'm Craig Smith, and this is Eye on AI. In this episode, I speak with Tinman Shu, a rising figure in the AI research community, soon to join Johns Hopkins University, with an impressive background that includes a postdoc at MIT and a PhD from UCLA. Tinman works at the intersection of AI and cognitive science with a particular focus on societal aspects of both human and artificial intelligence. Our conversation revolved around the concept of world models, a term rooted in developmental psychology and cognitive science, and their integration into AI. Tianmin elaborated on how these models, coupled with large language models, can enable the creation of agents capable of interpreting and interacting with the world in human like ways. He sheds light on his projects involving world models for household environments and the potential of multimodal sensory data in their training. The episode also delved into the challenges and future trajectories in AI, especially in the realm of social learning, where AI models learn alongside of and from humans. Tianmin discusses research driving the future of AI and human robot interaction, and I hope you find our conversation as insightful as I did. At home, at work, we all know one person who's password challenged. Sticky note reminders, emailing passwords, reusing passwords, using the word password as their password. Because data breaches affect everyone, you need 1Password. 1Password combines industry leading security with award winning design to bring private, secure, and user friendly password management to everyone. Companies lose hours every day just from employees forgetting and resetting passwords. A single data breach costs millions of dollars. 1Password secures every sign in to save you time and money. 1Password lets you switch between iPhone, Android, Mac, and PC with convenient features like autofill for quick signups. All you have to remember is the one strong account password that protects everything else: your logins, your credit cards, secure notes, or the office Wi-Fi password. 1Password generates as many strong, unique passwords as you need and securely stores them in an encrypted vault that only you have access to. I use 1Password, and you should too. 1Password's award-winning password manager is trusted by millions of users and over 100,000 businesses, from IBM to Slack. It beat out 40 other options to become Wirecutter's top pick for password managers. Plus, regular third-party audits and the industry's largest bug bounty keep 1Password at the forefront of security. Right now, my listeners get a 2-week free trial at onepassword.com/eye on AI. So, why don't you start, Tianmin, by introducing yourself, and then I'll ask questions from there. Give a little of your educational background and where you're working today and what you're working on.
So I'm actually going to join Hopkins, the CS department and also the CalSci department as an assistant professor. But previously I did my postdoc at MIT, and before that I did my PhD at UCLA. So I working at the intersection between AI and cognitive science. So I think a lot about not only building artificial intelligence, but also how human intelligence can inform us to build better AI. And I think that the idea of building a world model that actually originally comes from cognitive science. And then especially I have a kind of strong interest in the social aspect of AI and also human intelligence. So how we can build human level kind of social intelligence so that we can allow systems to understand human and really cooperate with human in the same way that we can understand and cooperate with each other. And again, I think that's something that's as one step aspect is very challenged right now, and also it's not something that big companies are working on. And I think it's also something that will really benefit from having a role model. both in the sense of understanding how human understand the world, and also how we can understand human that live in this world.
Okay. Can we start, first of all, by talking about world models? I've had a few episodes on world models, but maybe you can. When did the idea of world models emerge? I mean, I've been following Jan LeCun's work, but I know it's much broader than that. When did that idea emerge? And can you give us just a very brief history of its development?
So just a disclaimer, I don't think that the history that I can tell is probably not the full history. There's going to be some people at some point talking about world model that I don't know about. But the kind of history I'm familiar with is coming from developmental psychology and also cognitive science. So in developmental psychology, there's this theory about core knowledge. So it's actually a theory proposed by Liz Spelke, who is now a professor at Harvard. So she had this theory about so since birth we have some core knowledge about the world and about other agents that we can use as a foundation for developing more sophisticated intelligence that we can develop later in our life. And one of them is to understand the physical world. So, for example, we have some physical common sense like object permanence. We understand support. If you put something on table, it won't fall. So this kind of basic kind of physical common sense um, allow us to actually develop more sophisticated intelligence. And we have acquired those physical common sense very early on, maybe even through evolution. Now it's unclear like how much of it is actually come from evolution, how much it come from experiences living in life. Um, Now, there's also this idea about having an internal world model that can allow you to simulate what could happen in the future. And you can use that kind of simulation to not only reason about future physical states, but also plan yourself better through this kind of simulation. And that comes from a lot of, I guess, work from my actually PhD, sorry, not PhD advisor, postdoc advisor, George Tannenbaum. So he had this idea that human has this internal intuitive physics engine. So we all know physics engine, which allow you to simulate what could happen in the physical world. Now, human in our minds, we can have intuitive physics engine that allow you to simulate what could happen in the physical world, just like how you can simulate what could happen in a physical world using a game engine. Now, using that, they show that you can simulate physical events and use that kind of simulation results, adding some kind of noise on top of that. And you can use that to approximate how humans judge physical events pretty well. So they did experiments where they show a tower of blocks, and they ask people to judge whether the block will fall or not. If they will fall, which way they'll fall to, right? And then it turns out that if you actually simulate that using a game engine and add a little bit of noise on top of that, because people have imperfect kind of simulation, right? So a kind of physical simulation plus some kind of noise or some kind of uncertainty that approximate human judgment really well. And then I think there's also recent kind of collaboration with a neuroscience at MIT, Nancy Canwisher. They show that there's some kind of evidence in our brain that maybe our brain is also using actually the game engine to simulate what could happen in a physical world.
Yeah, and that engine to simulate. Um, what's the computer code or algorithmic architecture behind that?
I think one way to understand it is that you can generate, uh, you can write down code to describe a genetic process. So in this case, you can describe a genetic process as like a word model. So you sample objects, you kind of simulate force, and then the genetic model will tell you after you apply this force what could happen next will be the state of these objects you just sampled. So you can write down this generative process as a program. And then when you run this program, you will sample this sample from the generative model, and it will tell you what's the distribution of the, for example, in this case, what's the distribution of the future states of these objects after you run the simulation, right? So that allows you to, first of all, simulate through a generative model the world, and second, it gives you a distribution. And what you can do with distribution is you can conduct probability inference. So say if you want to predict where these objects will fall in the next few steps, you can use that simulation, that distribution, to tell you what is the likelihood of these objects falling into this place in the next few steps. You can also use this simulation to do planning, for example, with uncertainty. So I think probably this object is going to fall this place, but maybe also in that place, based on my simulation, based on the distribution coming from this probability program. Now, given this uncertainty, how I can plan myself in order to, for example, maybe catch these objects. Well, that's like one implementation, right? You use a physical simulation, and that allows you to sample future states, and that can be implemented as a probability program.
I see. And then in your talk, you were talking about combining world models and large language models. As and the language model would provide the reasoning, and the world model would provide the predictions of future states, and then the language model would pick which action for which to arrive at a future state. Is that right?
Well, we kind of explored or discuss different ways in which people have tried to use language model to implement as like a word model. So the most, I guess, direct use is, say, let's prompt language model with the current state, the action, and ask language model what could happen next. So this is the basic idea of a word model, right? You want to predict what happen given the current state and given our action. And then I think that the paper you mentioned is the reasoning as planning paper, the RAP paper. So the idea behind that is that why not we try to use language model to do this, to imagine what could happen after taking an action at the current step. It works to a certain extent. I think in some simple scenarios it can work. I don't think at this point language model is robust enough to serve as a one model on its own for more complex scenarios.
Okay, and then this most recent paper and the workshop at NeurIPS was about combining the language model with a world model. So the world model predicts the future states, and the language model provides the reasoning. Did I understand that correctly?
I don't think that's I guess the complete idea. So the idea is that we want to have explicit world models and also explicit agent model that's built upon world model, and then using agent model and world model we can conduct model based reasoning. Now we want to explore the idea that how language model could be as a backend to implement world model and agent model. And of course, like the RAP paper, yeah, there has been effort that try to use language model directly as, for example, world model and agent models. That can work in certain scenarios, but not in more complex scenarios. Now we want to explore, for example, how we can maybe enhance language model to serve as better world models and agent models. And second, we want to also explore ways in which we can not only just use language, but also use other modalities like the vision, like even like touch or audios to really build multimodal world models. That's so obviously that's not going to be the kind of typical language model you see nowadays.
Yeah. So can you talk a little bit about that? I mean, how you introduce the language model into this architecture with a world model in order to produce an agent?
So I think I would say there are probably like two ways you can introduce this. One way that's not coming from my own work. That's from my colleagues at MIT. So they introduced the idea that use language as interface to translate language description about scenarios into a probabilistic program so that you can conduct probabilistic inference using that probabilistic program. And again, probabilistic program serve as a training model of the world and also about other agents. So this idea comes from kind of very classical idea in cognitive science called language of thought. So we have our thought in our mind, and we think about those thoughts in the form of language, right? We can also write down those thoughts and use our language to communicate with others about our thoughts. So then if you do the reverse process, where given language about scenarios and also a question about that scenarios, how you can conduct reasoning using internal thoughts, not as directly as language reasoning, but you want to convert language into an internal thought and reasoning over that thought. So, for example, you can describe a language. You can use language to describe physical situations. Like I just told you, there's like maybe a, to- a, a tower of blocks on a table. On the bottom, you have a small block. In the middle, you have a larger block. On top, you have an even larger block. I can ask you, can you imagine how stable this top of blocks can be, right? I can also describe a different scenario. On bottom, you have a very large block. On the middle, you have a smaller kind of block. On top, you have a teeny tiny block. Then you can also imagine what could happen next. So notice I have shown you zero image about this, but you can, based on my language description, try to understand what I'm trying to describe here, right? So how we can convert that language into something like thought process that allow us to simulate what could happen next. So I think the colleagues at MIT, they come up with this idea that you can use language model to translate this language distribution into code, and specifically a probabilistic program that will basically become a physical simulation. So the scenario I told you, after the language model, you'll get a code that allow you to simulate the physical situation, and you can simulate what could happen next. And that this again allow you to do model-based kind of reasoning about the physical world. So I think that's very neat idea. And it's also very good use of language model because again, I don't think language model itself has all the knowledge about the physical world, but language model is really good at writing code, and we all know that. So, and then again, it kind of translates, kind of do this in reverse process where you can convert language into a thought.
That's really interesting. And then and you guys have done this. This isn't theory. You've built these models to work together. What is the agency layer? I mean, that's the reasoning and the planning or decision making. Then how do you add the agent on top of
Right. So, so agent is modeled as a decision-making process, basically in this framework, where you have your world model, your internal world model that you can use to simulate what could happen. You have your own goal, and goal has a condition on goal. You have a reward. So your reward will try to help you to reach the goal, but also in the process minimize the cost. And then you have your belief about the world because an agent only has partial observation of all of the physical environments. You don't know everything. So you have a belief about what the actual physical state is. So again, belief is like a distribution of the physical states. Now, condition on this, then you can try to make a plan that can I guess based on your first of all your belief about how the actual physical states look like, and then also try to maximize your rewards that allow you to reach the goal after doing simulations about different kind of plans.
Yeah, so I'm trying to think of it in so that's an RL reinforcement learning engine in effect.
Well, that doesn't have to be reinforcement. That can be a model based planning. So the idea behind The model-based reinforcement learning or model-based planning is that you don't need to do a lot of trial and error in the actual physical environment. You can do so using a simulation. You can simulate beforehand what could happen after taking different kind of actions. Then you can search for the best set of actions that allow you to reach the goal without actually trying out in the physical world.
At home, at work, we all know one person who's password challenged. Sticky note reminders, emailing passwords, reusing passwords, using the word password as their password. Because data breaches affect everyone, you need 1Password. 1Password combines industry leading security with award winning design to bring private, secure, and user friendly password management to everyone. Companies lose hours every day just from employees forgetting and resetting passwords. A single data breach costs millions of dollars. 1Password secures every sign in to save you time and money. 1Password lets you switch between iPhone, Android, Mac, and PC with convenient features like autofill for quick signups. All you have to remember is the one strong account password that protects everything else: your logins, your credit cards, secure notes, or the office Wi-Fi password. 1Password generates as many strong, unique passwords as you need and securely stores them in an encrypted vault that only you have access to. I use 1Password, and you should too. 1Password's award-winning password manager is trusted by millions of users and over 100,000 businesses, from IBM to Slack. It beat out 40 other options to become Wirecutter's top pick for password managers. Plus, regular third-party audits and the industry's largest bug bounty keep 1Password at the forefront of security. Right now, my listeners get a 2-week free trial at onepassword.com/eye-on-AI. Right. That last part sounds like a little bit like AlphaGo, where you simulate various courses of action and then uh, you search for the optimal solution and implement that solution. Is it similar in architecture to AlphaGo? I mean, the AlphaGo, it's not using a world model.
Okay, so so what is the core component of AlphaGo? It's the Monte Carlo tree search, right? So that's a planning algorithm. That is not RL. That is planning. And then the reason why you can do planning in that case is that you know the rule of the game already, right? So you know exactly this will be the next state of the game after taking certain move, right? And that allow you to do forward simulation. You can think ahead for many steps and get the better plans by doing this kind of imagination. Now, you mentioned that there doesn't seem to be a world model. There is a world model. The world model is very simple. It's just the rule of the game. You know, and then you know exactly what could happen next. Now, the more and I think MCTS kind of a planning algorithm is very uh, kind of intriguing because it's very general in the sense that if you have a reward, if you have a world model that allow you to do forward simulation, in theory you can do anything, right? Um, if you do enough simulation, you can get pretty good planning. And if you add a little bit learning like AlphaGo, you can also make the search even faster. Now the downside, the challenge is that in the real world, you don't have that perfect world model. But if you do build a world model for certain domains, then you can plug in that world model to do Monte Carlo research or any kind of model-based planning.
Yeah. How far have your implementations of this gone? I mean, you've built a model with all these elements. Uh, does it depend on does its efficacy depend on how large the model is, as is the case with language models, that the larger the model, the better performance? Or is this more a matter of just optimizing hyperparameters and stuff like that.
Right. You mean like building, actually learning a role model that can be used for, I guess, learning a role model that can be used for very broad set of domains and not just like specific domains. I think we are not remotely there yet. The reason is, for example, there's just so many different kind of things you can model in the world, right? You have so many different objects, and even if you think about one specific object, they have so many different kind of properties you can try to model, like the materials, the textures, the weight of the objects, the shape, and all these different kind of properties, right? And depending on your task, you might need to model the objects in different using different representation of the objects. So, for instance, if you only want to say carry some box around, you probably only need to know the weights and the rough shape of the box. You don't need to know uh, very detailed kind of a representation of the box. If you want to manipulate fluids, for example, I don't think shape and weight will be enough. You need to actually model fluid as some kind of particles and how the particle will flow and will interact with different kind of surfaces, right? If you want to say how I can manipulate some kind of deformable object, so say if you want to cut some vegetables, then you also need to know like how the vegetables will interact with the knife, and then how they will maybe in some cases maybe a roll on the cutting board, so you need to somehow hold it. So there's a different kind of representation for this like if you only think about single objects. Now, if you think about broader case where you have many different objects in the world, that's not only having different kind of properties, but also being also they are dynamic. So their states are also changed by the forces in nature, but also other people. So, for example, objects may be moved by another agent while you're not present. So now you need to also kind of imagine where the object could be. So one model will become very complex in the real world. Now, how we can build that, I don't think there's a single answer yet. Um, we have world models that can work pretty well in certain domains. So I mentioned that for robot manipulation, for example, we can learn how some kind of substance or methods objects will uh, change how their state will change given certain actions of the robots. And using that, you can try to manipulate robots for certain tasks. I think you mentioned Gaia. So Gaia is another great example of a domain-specific kind of world model. Of course, you can use that to maybe build self-driving cars, but you cannot use that for, say, object manipulation for robots. Um, we have other cases where, for example, you can learn a world model for um, um, like some kind of abstract kind of knowledge. So there's some world model that's represented as a knowledge graph. So say if I do this, what happen? Like say if I want to take flight, I need to buy a ticket first. So some kind of abstract kind of common sense knowledge. Now you can use that to do certain things. So say like maybe help you to make a plan for vacation. But again, that's because it's representing it as like abstract knowledge. You cannot use that for physical manipulation. So I would say I don't have a great answer about like say building a single world model that can represent anything in the world. I also don't think at this moment is the best strategy to try to build such a model. It's probably better to say a world model that can do well in a range of specific domains. That's and also you can easily generalize that to similar domains and fine tune it with a small set of data. But I don't think it's the best strategy yet to build one single world model that can do everything.
Right, and the models that you've built are trained or tuned for what domains?
Right. So specifically, we've tried to build world models for household domains. So we have built at MIT in our group at MIT, we built a household simulation called Virtual Home. So we can build different kind of apartments. You have different kind of objects in the apartment you can interact with. You can put many different kind of agents, simulated agents in those environments that again you can interact with. So in those simulation, we can generate embodied experiences as training data to fine tune this, for example, language model or different or other type of model as a world model. So this is a very different from, say, training a language model on texts and hoping you can get some knowledge about the words from those texts. Because again, just intuitively speaking, for human to understand the words, I don't think you can just read books and you can perfectly understand what could happen. There are many details about the words that won't be described in text. So say, what happen if I push push this button of the dishwasher, or what happen if I open the cabinet door, put another object into the cabinet, and then go away. Couple of days later, I come back. How many objects will be there in the cabinet? Those kind of knowledge are very common to us, but you won't read it from the books. But again, those are kind of common sense knowledge that even kids can have. So, but if you, but the idea here is that if you build embodied agents in those simulation environments, ask them to do different kind of tasks, interact with different agents, or even just do random exploration, they'll get these experiences, right? You'll get, say, what will be the so how many objects will be in the cabinet after I did this sequence of actions. What will happen after I push this button of the dishwasher? What happen if I say, we haven't done that yet, but let's say what happen if I talk to someone and then tell them that I'm pretty happy today. Let's hang out. Maybe in the afternoon. What will be their response? So, but if we can simulate all this and get a lot of this experience data, then we can train a model that can really understand how the world works, or even how people will react to actions.
And for training in a specific domain, is that done uh, through video or still images or text, or what is the data that you're using to train, for example, a household?
Technically speaking, you can use any kind of data that you can get from the environment. So we have the vision data for sure. You can have the Guangzhou state of the objects and agents. You can translate those Guangzhou states into language. So say how many objects are there inside this cabinet. You can also there's some simulation that allow you to also simulate audio. So you can say, if I drop this uh, ball onto the ground, what will be the sounds that I can get? You can even simulate touch in some systems. So I think actually in the same group at MIT, they had a collaboration with another group that works on multimodal sensory. So they have this Nature paper in recent years where they build this glove that can allow you to simulate, allow you to get touch sensory. So now imagine if you have some kind of VR set up where people can using this kind of graph interact with different kind of objects, and can give you this kind of even the touch sensors. Then you can use those different kind of multimodal sensory data to train your world models. We haven't gone that far yet. I think so. So the work I tell you about, we are using the Guangzhou state of the objects and agents to and then translate that into language, so we can more easily to train that language model to understand the world. We have also done in another project we have done this. So again, we are using the states that we can extract from the images. So particularly we represent a state in the environment as a scene graph. So scene graph is this structured representation about the world. Each node is objects. Each edge connecting two nodes, representing the spatial relationship between two objects. So if you have a cabinet, you have cabinet nodes. If a cup, you have a cup node. And then if the cup inside cabinet, there will be inside the edge connecting the cup and the cabinet. So this kind of representation can be extracted from images, but it's a pretty appealing kind of representation compared to pixels, because from pixel you don't get this semantic knowledge about the physical states. Now you don't need to represent it into language, but you can just use the symbolic representations, this scene graph, as the word states. And again, you can train language model on top of those symbolic representations to predict, for example, what will happen next.
Yeah. During that training process, I spoke to somebody a year or so ago who was working on a training system that was hyperspeed. So 100, I think it was 1 million frames a second or some incredible rate. Do you have to train in real time, or can you train at hyperspeed? How long does a system need to absorb an image or a frame of video?
So I think that depends on how data hungry your model is. And so say if you want to train model free RL, I think you mentioned this, right? So usually for training model free RL, you want your system to be as fast as possible because it is very data hungry. You have to try many different actions just blindly, only just blindly, so that you can get enough data to or enough training signal to update your policy. If you haven't tried enough, you probably cannot even get any positive reward at all in some very complex tasks. However, I think for training world model, on the other hand, I think the speed is actually not the biggest issue. You can just let an algorithm, or not algorithm even, just like add any kind of embodied agents in the simulation, let it to explore, try different things in the environment for first a period of time. You're gonna get a lot of data already, because again, it's different from training RL agents, because RL agent has a reward function that defined for specific goal. You try a lot of things, you get a lot of observation data, but none of those probably at the beginning are related to your task, so you don't get any positive reward at all. However, for training world model, you train a lot of random things in the world, a lot of random things will happen, and those random things happening is actually all the useful training signal for your world model, right? If I put something will be moved. If I put something down, something will be in a different location. If I walk from one room to another room, I know my location will be changed. My observation also will change. So that gives you many training signals you can use. So you don't need to, I think, compared to at least model free RL agents, you don't need to try too many steps to get useful data.
So you've trained in a household environment for that domain. Is this all in simulation, or do you have you or is this outside of your area of research? Have you tried controlling a robot with this kind of a language world agent model?
I guess part of my research is also in human robot interactions. So down the line, we do want to evaluate all these models in the real world. Recently, I haven't done that yet, but there are other groups that have done that. So I think we actually mentioned this paper in our tutorial. So there's a very recent paper from AI2. So AI2 is AI Research Institute in Seattle. So they show that if you want to train a robot policy for indoor environment kind of navigation. So they try to find a TV remote for me, or try to train some policy to do very simple object manipulation. Say pick up one glass and give it to me. And then they train it actually on raw pixels. So they don't actually train on Guangzhou's world state. So given pixel that we can see in front of you, and then give a command, say like find this object for me. You want the robot to actually navigate and search through an apartment and find an object for you. Now, previously people think there could be a very big domain gap between simulation and the real world. In fact, I think many robotics researchers are actually against using simulation precisely because they think no matter how good simulation is, they're not going to be real. They're going to be 100% real. And particularly if you think about the kind of policy you want to build here, it's crazy, right? It's actually raw pixel input and directly map it to some actions. Now the pixel rendering from the simulation will be definitely not going to be 100% real compared to real world images. However, they show that if you have enough data, you actually do not need any kind of real world data to fine tune the model you're training in simulation. And directly they can deploy in real world apartments. And that's the real physical robot to do the same kind of task. So I think that's very promising because the quality of the current simulation is already very good. That's one. And second, it allows to generate a lot of data, a lot of data you cannot get from the real world. And if you have enough data, you can get very kind of good policies out of it. And I think it also presents maybe even the third kind of opportunities. So when you have a lot of simulations, you have household simulations, you have traffic simulations, you have those kind of objects manipulation simulation for robots. You have fluid simulation. You have other kind of physical fixed engine kind of simulation. You have all these simulation people have built. You have a model that can understand, learn like general knowledge about the world from all these different simulations. Then those kind of knowledge are very useful for the real world. Even though like for individual simulation, they don't represent the whole world. But if you can combine knowledge from different kind of simulation together, then you can have I guess like a fuller picture about how the physical world works.
This is all still in the research phase, but how long do you think before? I mean, this is one kind of agent. There are a lot of different strategies to build agents. What? How long? How promising do you think this method is as opposed to others? And how long do you think before somebody puts refines this and puts it into a product in the real world? In
Right. Well, I guess like you mentioned Gaia, so I don't know exactly how they are using their simulation for their products, but they are startup companies. I don't think they're gonna build anything that's just purely for research and have no real value at all. And then I think also we have things again like I mentioned these indoor kind of robot navigation kind of tasks, right? Those are very useful, right? If you want to build robots systems that can help you to do household tasks. Um, one of the most fundamental tasks you're going to ask the robot to do is to find objects you're going to need for whatever the thing you want to do in the house. Now, down the line, if you train robot to do more complex tasks using similar kind of approach, I think will be a pretty kind of compelling kind of products for you. And then that's definitely going to be more useful than a Roomba for sure. And I think that another thing that could be very useful is not just embodied agents like robots or self-driving cars, but also just like say web agents. So think about web interface or any kind of software interface as also a world model. Like you can try to figure out how those interface can work after you taken some actions, and you can model it as a kind of virtual world model, so to speak. Then if you can learn that, you can also build any kind of system agents for web interfaces, for softwares, etc.
and so, do you think that within a year or 2 years or 5 years, there'll be, whether or not they're embodied or virtual, there'll be people will be working with agents built on this architecture in various domains.
I am not great at prediction, but I think embodied agents are always very hard to build. Like for example, you would think the one of the most one of the most basic kind of task for robots, which is grasping an object. Um, I think some robotics actually previously says that whenever you start to work on grasping, you can have a whole career ahead of you. It's just a very hard problem right now. Um, However, if you think about simplified tasks that doesn't require a lot of very complex physical manipulation, like say maybe like web interfaces, or some kind of virtual assistants that can help you to do some tasks. I think that could happen easily. I think there are already people trying to build such products as well. Um, and I think also maybe even like say for embodied agents, for very very kind of not very very but somewhat restricted environments. So say like like in a I don't know like warehouses or factories. Again, there are already you know products like that, but I think with better kind of uh, AI models, you can have more powerful kind of robot coworkers, so to speak, in those more restricted environments.
Yeah. But do you know of any commercial enterprise that's taking your research and implementing it?
Um, right now, I don't think so. I don't have that knowledge yet. Yeah.
Yeah. Yeah. It's fascinating research. So I see. Do you refer to it as language agent LAW law
Right. So, language model, agent model, and word model.
real model?
Yeah.
Yeah, uh, yeah. I mean I see that LAW. I don't know if that's
Law.
a term that you
Yeah.
use. Okay, so what's next in your research?
Well, so like I said, building world models and also agent models. I think that's very I guess fascinating direction for me and also for many people now, and hopefully even more people will find it fascinating and work on that. But I think another thing and I'm really interested in is social learning, which was also taught a little bit about in the tutorial. So you have model that can learn on its own, but think about human actually learn a lot of things with each other or from other people, right? And we can also teach knowledge we learned to other people. So how we can actually build models that can or agents that can also learn with humans, learn for human, or learn from humans. I think that's another kind of direction I really want to work on.
Okay. Well, we're over 45 minutes, so this is probably enough. I really appreciate your time, and on such short notice, it was a fascinating tutorial, and I'll watch your work going forward.
Yeah, thanks so much. I had a lot of fun talking to you today.
That's it for this episode. I want to thank Tianmin for his time. If you want to read a transcript of today's conversation, you can find one, as always, on our website, eye-on.ai. In the meantime, remember, the singularity may not be near, but AI is changing our world, so pay attention.